All right, so let me give my 5 minutes talk. Let me see if I can share my screen. Here we go. And okay, so I am Hiroshi Maruyama, working for Preferred Networks. Let me give a little bit discussion about the terminology. There are sometimes these words, AI, ML, software 2.0, used interchangeably, but I think it is important for us to make a clear distinction between them. So for me, AI is a research field, and it's not a system that uses AI technology. Of course, we have the technologies coming up from the AI research, but I think we should better to use a different word for the technology rather than the research field. Machine learning is, of course, one of the technologies for inductive programming, and it is based on statistical modeling. Software 2.0 is a new paradigm in automated programming, and I am going to a little bit go further in this view. So software 2.0 is, I think, the attempts to automate the programming, and by searching the programming space. So traditionally we did a programming by manually coding the program. On the other hand, in software 2.0, programming space is over here, and you search this space, the solution which satisfies the given specification. And of course, we have to have a lots of computation behind that. So speaking about, so that it's very important to be able to give the specification, okay? Then let me briefly review what we have done in specifying what the program is. And one, very, very basic way of specifying the program is just coding, writing the code, or by specifying the execution steps. Or in a traditional software engineering, we have the model-based software development, which means you give the mathematical model, and that is semi-automatically transferred into the execution code. But assumption behind this method is that we have the complete specifications, or we can write the complete specifications. But then, the world is much more complex, and sometimes we have to give the specification by input to output examples, and we have a test-driven development, and also we have a statistical machine learning, and this is part of software 2.0. Sometimes we give a specification by giving external oracle. So reinforcement learning using the external simulator is one example. Or agile programming is a kind of external oracle. Our customers says this is no, I don't like this, and you got that feedback and do the programming again. And this is a manual, but reinforcement learning and other optimization techniques are more automated. But important point is that we handle the situation where we have the incomplete specifications or conflicted specifications, and that's the a very difficult point in software 2.0. So that's why I believe we have to have a new engineering discipline. Let me give an example of another engineering discipline called civil engineering. When you cross a bridge, you don't much worry about the bridge is falling down, because there is a big body of knowledge called the civil engineering behind it. And these are the volumes of the civil engineering handbooks. And most of the pages are spent on the theories, like structural theory or material theory and so on. But there is a very small table called safety factor. And this is a safety factor table. And I think the point here is that the civil engineers know a lot about civil engineering, but they also are aware that their knowledge is not complete. That's why they have this safety factor table. And if you apply this safety factor like 3 times more strength than the theory says, once you get that point, then you can convince the society that the technology is mature to be adopted by the society. So I think the same thing should be done here for machine learning. And of course, we don't know much about the we have the incomplete knowledge why this machine learning system works. But by demonstrating the usefulness of the machine learning systems and the safety and so on, by doing that, I think we can convince the society, and that's why we are here. We are discussing about machine learning engineering. That's my position. Thank you.
Thank you very much. Thank you very much. Interesting. We will touch on that in the discussion. So second, Liam, Mohamed.
All right, let me share my screen. Okay, so for my talk, I actually thought during this workshop that most of the previous talks covered the superset, and I'm gonna try to get something new. And I've been thinking about this for the last 5 minutes, like what are the new things I can provide in my very first talk. So first, let me just quickly introduce computing with data. So besides my work at Cisco as director of AI, I also I'm teaching assistant part-time at Stanford University, and I like writing a lot. So this book is co-authored with Guy Lebanon, and basically we try to maximize the overlap between two disciplines, data science and software engineering, not just data engineering, but software engineering. And I really liked from Jacomo's talk, the point about like bringing these like two disciplines together. There's going to be a very interesting intersection between them. And if it's not necessarily for creating a new discipline altogether, at least overlapping of knowledge and overlapping of understanding of what it takes to build an entire pipeline that solves an AI-based or big data-based problem. So for my talk, I wanted to focus more on the dev ecosystem 2.0. I think the idea of having, by the way, great survey of like what startups and horizontal platforms are there. And I think it's a great starting point to have this progression, an increase in the ecosystem, flourishing ecosystem for helping AI solutions. But I also couldn't help but like feel that the fact that we can actually summarize it or put it all in one slide is sad, because we need the explosion that has happened for traditional software, rule-based software. It's going to be much, much harder for you to go and figure out that map for all the systems that we have today that allow us through the life cycle of software 1.0 to produce something and make sure it's like verified, and you get through the entire like speccing, development, deployment, monitoring, debugging. The ecosystem is of course huge for the 1.0 ecosystem for development of the rule-based systems. If you think about how we can like look at the stack or the ecosystem, if you think of hardware challenges, we have had a lot of AI accelerators, right? So the TPUs, GPUs, what have you, have been built specifically, including like your phone now and the new MacBook. They have neural engines and so on. These accelerators are great for the ecosystem. They allow us to do way more in much less time, but they also bring about a new set of challenges. Like back in the day when you have, let's say like, a basic bug, that you file a bug and you say like, here's how to reproduce that bug for a rule-based system. A lot of the times you include in the bug details the hardware and the software version and the SKU and certain ways or certain conditions under which if you repeat the same reproduction steps or reproduce the steps exactly the same way, you will find the bug again. So with AI and specifically with these like highly parallel systems, like think of a GPU when you're doing a simple thing like floating point sum, right? It's non-deterministic. You can run it multiple times and you get multiple results because of the precision and the parallelism constraints we have, or because of the way we actually represent the floating point. It can change based on the order of which you aggregated them and yield a different result. So there is a lot of like interesting challenges that have been kind of abstracted away in traditional software, but now we have to be very careful about. Speaking of which, thinking in probabilities. So as you mentioned in the workshop description in previous talks, rule-based systems are deductive. You can have like TLAs or other like, systems for verification. And you can show even for a distributed system that it works correctly. And you can prove that. We're thinking of inductive systems. We're thinking of like how to reason about the world via a sample, and you get some probable output, and you're basically trying to verify that this is more or less within the boundaries of what you expected that system to produce. So we have to design for safety, and I really liked the previous talk talking about the safety factors, and we learned a lot, like resonance frequencies, and we had disasters and bridges, and that's how like these things became an acknowledgement of like, we don't know what we don't know, and we have to like provide some safety net or some guardrails for the future, just in case we miss something. It's an incomplete knowledge, so you cannot make complete deductions or complete conclusions. And for that, we think of like applications of, let's say, generative models. If you have a generative model that produces text, or even a speech model, like a speech recognition system producing text, and there's a probability that it might erroneously produce profanity. Imagine if you're just speaking like I am speaking right now, and there's closed captioning and it starts writing or displaying profanity because it made a mistake. Well, your safety net should avoid that embarrassment by masking out these kind of embarrassing errors and making sure that you do not go into that territory. So you need some sort of guardrails, and I would say these are going to be rule-based, of course, and super important for controlling the output of what these non-deterministic systems can produce. I also think of GitHub and just all of these systems that we had popularizing open source and collaboration of software. Specifically, like if you think of of course we had SourceForge and other things before, but the role they play in the ecosystem is extremely important, because they show you like a rating and collaboration environments where multiple developers can come in and collaborate on forks of the same project and so on and so forth. We need something very similar for data. We need a kind of data hub where you can imagine like in GitHub when you have like the lineage of the code, right? And the change sets and how like each change affected the rule-based system. You need some sort of data lineage as well for data systems, understanding like how to reproduce your DAG, your kind of workflow or pipeline, and the ability to fork the data and verify that it works for your own fork and so on, but also the ability to trace back, just like you have blame in GitHub, the ability to trace back data lineages. Like we mentioned that multiple times during the talks, that your code is basically writing itself using the data, right? So how can you go back and then point exactly which change in the data set or the other code artifacts caused your system behavior to change over time? And the other dimension of the GitHub-like systems is they made integration with the rest of the ecosystem much, much easier via webhooks and CI/CD integrations and so on. So the development cycle became much easier for the ease of integration that it provided. And we need something as easy for data science and AI projects where you can actually integrate CI/CD kind of pipelines, but instead of thinking of how you can test like a unit test and integration test, how to do a probabilistic, maybe statistical test, right? Like thinking of the, maybe a t-test for your data that you captured in test eval, and subsampling from production data, and thinking of like, okay, do I have concept drift when I'm releasing this? Is it going to cause any issues for the new deployment, and so on? So if you think of the other ways of testing, you can think of simulation testing. We talked a little bit about self-driving cars, and you might have a new modification in the system. So instead of waiting on going outside the real world, you can build a city and simulate, like, within bounds, did the system operate as expected or not? These are all interesting, modifications to existing ideas. I don't think there's anything that's extremely novel. The challenge is the ecosystem is not there yet. We need to build these systems and make them as easy to integrate with. And maybe there's a little bit of a mindset shift, or a paradigm shift in the way we think about these artifacts as well. So there's tracing and logging, observability is extremely important, profiling. These apply to traditional systems as well, but they became more important now when you do not have a full understanding of coverage. Like when you're designing the system for a traditional system, you can think of corner cases, combinatorial testing, and you can figure out here's my domain and range. And you can easily assert that these things map to your expectations. But with the ever-changing behavior and the very long tail for all of these problems that AI provides solutions for, it's going to be much, much harder to test for everything ahead of time. So even though you walk into the design room with specs and thinking about the tail and how can we provide safety, you cannot assure, without certain observability that you have been able to see all of the possible outputs, and you need to understand that sometimes in real time with monitoring and profiling. And instead of just looking at memory print and kind of CPU use and exceptions count for traditional software, in addition to all of this, you also have to look at the input distributions and output distributions, understand emerging trends, unique values, why did they produce such things, and maybe the classes that you have shifted. The concept drift is extremely important, and not just in data, but also in the labels that are in the real world, and how can you make sense of these. I think observability overall is the line of defense that you have to have. If you have weaknesses in the rest of the system, they will, at least by the mere act of observing what's happening, will push you to think more and more about where else do I need to fix things. So in conclusion, I think I did not coordinate this with Jacomo, but I think we have the same sentiment. We have somewhat mastered software 1.0, and we're still clueless about AI and data sets. It's just going to take time.
Thank you. Interesting stuff in there. The need for a lot of engineering to actually try to compensate the limitation of the current ML models that we're having. Lyle, do you want to pitch?
Hi there. So my name is Liam. I'm a professor at the University of Montreal. I don't do screen sharing, so you can just maximize me. So I'm going to talk about something a little bit different. I think there's a lot of interesting connections. I've really enjoyed a lot of the talks we've had so far from all of the panelists. So let's go. So I do robotics and deep learning, and I put software 2.0 in the title because I felt like I had to, but I don't really know that much about that. So, but I've learned today, but thank you, Foutse, for inviting me. So the objective, in robotics is to take, robots from environments that look like this and put them in environments that look like this, right? And to date, the number of actually successful consumer robots that actually have deep learning systems on them is extremely small, very, very limited. So a traditional robot system has a certain set of abstractions. So the normal way that we do it is we separate the world from the plant, and the robot is the world and has actuators, and it exists in an external environment, and it has sensors. And then it perceives the environment through the sensors. So we need a perception system. This is actually the area where deep learning has made the most inroads so far. Then we have to take all these measurements that we're getting from this perception system and assimilate them together into a coherent estimate of the world. And we have to use that estimate to make a plan about what we're going to do. And then we send that plan to some kind of controller and we actually execute control commands. And the nice thing about these traditional paradigms is that we could make like a very common theme that's been repeated in this workshop so far is that we could have guarantees about a lot of the things that came about the contracts between these abstractions in this like typical approach. So what are the desiderata then for a data-driven robot? Well, the first and foremost thing is that we have to guarantee that it's safe, particularly if it's a safety critical system like a self-driving car. And this guaranteed word is like a very hard word, right? Like, what does that actually mean? In practice, it means probabilistically guaranteed. We want robustness to real world nuisances. So when we take it outside, it doesn't matter if it's raining, it doesn't matter if it's sunny, if the sun's right in the camera, whatever, if there's like a giant lightning storm, or if you're at the top of Mount Washington, it's supposed to work in all of these situations. We want both the environment to be able to scale in complexity and also the tasks that a robot can perform to be able to scale in complexity. This whole thing has to run in real time. So this has to be like on embedded GPUs and stuff. And then like last and maybe most important in some scenarios is that we have to have some realistic way of getting a data set. And for physically embodied systems like robots, this can actually be really challenging because getting the scale of data that we need to train these systems can be laborious and dangerous and stuff. So I'll give you just a quick overview of what we do in my lab. So the research themes are trying to address some of these challenges. We try to build and learn efficient representations for robots. We try to think about and quantify and reason about uncertainty, and I'm going to talk about that in a little bit. We try to build efficient pipelines for learning and simulation and transferring that knowledge to the real world. And we also think really hard about evaluating robotics benchmarks along the same line that like reinforcement learning has been held to this standard now that it needs to be reproducible. We need the same standard with like embodied physical systems, but it's extremely challenging. In applications, I've worked on autonomous driving. In particular, I work on this problem, simultaneous localization and mapping a lot in my career. I won't get into the details. And now I'm just starting to think about manipulation in more complex, higher fidelity tasks. Okay, so let's talk about safety, right? Like this is the thing that's supposed to be the reason that we're making this autonomous car, even though as like a quick sidebar, it's really not. So everyone wants to like talk about this trolley problem, and we can think about like really connecting it with the first keynote. Like there's been decades of work of formal verification of how we can guarantee safety, and everybody wants to talk about how the self-driving car is going to have to make a decision about whether it kills a grandma or a baby in a stroller or whatever. This is like largely unproductive, I would argue, but there is a version of this problem that is productive. So I'll put it to you as the probabilistic trolley problem. So let's say you're in a situation where you have option A where you kill a pedestrian that's on the road but shouldn't be, so it's not your fault. And you have option B where you swerve and you kill somebody who's on the side of the road and you kill them and it is your fault. And there's some probability P that you'll kill this person B. You're going to kill the pedestrian with probability 1, but it's not your fault. So this value P really matters. If you're guaranteed to kill somebody if you swerve, you're definitely not going to swerve because the person in the road, it's their fault. They should admit more blame. But if there's 0 chance of you killing anybody if you swerve, then you're definitely going to swerve, because then even though it's this guy's fault, poor guy A, you can still save his life. And so, there's some like there's a decision value here for this value of P, which is why I find this problem really interesting. But the underlying thing here is that a prerequisite for even thinking about this problem is that we have calibrated estimates of uncertainty. And this is really hard to get from deep neural networks. So we've been thinking about this a lot in the project that I have with Foutse. We've been talking about the different types of uncertainty that you can think about in deep neural networks. And they're very different than traditional systems, because now not only do we have the uncertainty associated with the underlying process, we also have a certain uncertainty associated with the model, whether your model is trained enough, whether you're in distribution or outer distribution, and how much you can trust the output that you're getting in a specific scenario. And these things are very hard to predict and especially hard to calibrate, which is like a different issue. Okay, so point 2, the role of simulation in robotics. I think, roboticists always viewed simulation through an ambivalent lens. Like in one sense, it was just a plaything that unless you did it on the real robot, you weren't a real roboticist. That's the way it used to be. But now we have these robots, these simulators, sorry, that we can actually use to teach robots things. And then we can transfer that knowledge onto the real robots. So we can really save time. But how to teach them is actually pretty tricky. So we might show them how to do something. We might use reinforcement learning. On a real robot, this gets really expensive and slow. So this is an amazing project that was built by Google where they had like, I don't know, I forget the number, like 20 of these arms sitting in a room for like 3 months, just picking and placing objects, you know, all day long. But the ideal would be if we could actually train this thing in simulation. So I don't know if any of you seen this amazing video of this robot doing the Rubik's Cube, but this was trained about like 98% in simulation and then 2% on the real robot. And so this overcomes a lot of the problems associated with working with real hardware. Unfortunately, the value of data that you get out of a simulator is significantly like less than the value of data that you get of actually doing an on-policy rollout of a robot. And then somewhere in between those two is what I would call like off-policy rollouts, which is actually what we get, say, if Tesla collects all the data of people driving, like it's not the actual learning agent that's in control of the system. So it's like another agent, an expert that's giving them data, which is very useful for sure, but also imposes some distributional shift problems. So there's sort of two main approaches that we're investigating in my lab for crossing the reality gap. And these are like, I don't think that there's like this is a more general problem than just transferring agents from simulation to real. Really, the two approaches are you can somehow learn the mapping from one modality to the other. You actually explicitly learn it. You know that there's a data distribution shift and you learn what it is. Or you learn to generalize across. And so in the first case, like a lot of people use kind of these GAN type models to actually make the two data regimes, either simulated or real, be indistinguishable. And in the second case, maybe you use something like domain randomization that makes your system robust. Okay, last point. I know Foutse, I'm over. I knew I would. So just thinking about actually, evaluating and benchmarking a robot, a physically embodied system. So you like a lot of the problems that you guys are talking about, they're already really hard, but now like adding that element of evaluation and benchmarking onto a real physical system is even like another degree even harder because you can't standardize the environment. It's very hard, like when you're outside of lab settings and things like that. So in this frame, we've actually made a sort of an effort to build benchmarks and start a conversation, particularly around autonomous driving, and to get people from a wide variety of different backgrounds to think about and talk about how we can actually evaluate progress short of just looking at the latest YouTube video that Elon Musk has published and trusting that that's how well the system works or whatever. So this is a AI driving Olympics competition that we have run now at NeurIPS, which is a machine learning conference, and ICRA, which is a robotics conference for the last 3 years or so. And so in this setup, we have a simulator, we have this toy little robot. We can evaluate your agent in the cloud. We can evaluate your agent in a remote lab that's standardized. So you can just like remotely submit your agent and it'll get evaluated. We have a simulator, we have logs. You can do whatever kind of machine learning pipeline you want. We provide baselines and everything like that. And to somebody else's point, I forget who, but like somehow like standardizing things, I think it was Mohamed, the making this barrier of entry for getting some kind of standard reproducible machine learning pipeline in place and actually evaluating it in a standardized environment, I think is like very hard, but I think we're on the road to doing that. So this is like a time lapse thing. That's basically all I had for today. Thank you so much.
Thank you very much. Thank you all. Very exciting. So now we still have time. I got information that we can go a bit over time for discussion. So we still have time for some discussions. So if in the audience, anyone had a question, just raise your hand or use the QA. While we're waiting for question, I would just allow Jacomo to quickly summarize his point because we already saw it on the slide, but maybe just quickly summarize your 3 key points that you had, and then we'll kick off the discussion, if you don't mind.
Yeah. So thank you very much, Foutse. I mean, I think the key point that I was trying to make, and I mean, in line with a number of the other points that were made, and even harking back to Clark's talk, we're increasingly seeing the right way in which to build safe and secure and correct ML systems by having a lot of the implementation complexity move into artifacts that sit outside of a specific model pipeline. And so this is really what we mean by tooling and platform enablement for how we think about designing, building, and deploying machine learning in the real world. And it's happening, as I mentioned before, it's happening everywhere, for a broad category of data science applications, many different techniques. I mentioned the NVIDIA Merlin framework for recommender systems, of which there are many. We're seeing more and more deep learning frameworks, even for tabular data, in ways that are substantially changing how we think about building models on top of tabular data, of which TabNet that I mentioned before is one. But we're also seeing even I think I can send on the chat to attendees like something like reinforcement learning as a service, right? Even black box optimization, like think of VZA available as a service on GCP. We have explainability increasingly like available as a service. And again, these are just exemplars, but they are in a way ripping out a lot of the technical complexity that would otherwise have to be navigated by every single development team looking to develop that next model. And so Foutse, to your question before, I don't know that this is certainly not making things foolproof. We need people who understand what they're implementing and understand all of the things that can go awry, but just making, let's say, the surface area of complexity that people have to navigate, reducing the size of code footprints, I think starts to introduce some of the safeguards that we need in order to be able to do this well and to build ever more robust systems. And again, the main thing that we're seeing here is increasingly, one of the ways in which we're seeing more and more ML make its way into the real world is by becoming more and more integrated into, what are otherwise other kinds of software systems, right? So ML is just a specific, a technique and set of tools by which we can get at specific features and functionality within that software. I'll pause there.
Okay, thank you. Thank you very much. So while we are waiting question for the audience, maybe I will kickstart our discussion. I want to come back to one of the recurring themes across all the pitches, which is the safety. Right? So it turned out we're trying to build complex systems, sensitive system with a quite brittle technology, right? And we need to reach safety. And somehow currently we're using engineering to try to compensate for the limitation that we may be having around the technology. So my question for you is, do you think we can achieve a acceptable level of safety just by engineering, tooling around the machine learning pipeline? Or we need to maybe go back to the way we are learning as well and try to do something there? Like what do you think about it? Where do you think we should be putting much of the effort here if we want to achieve this goal of safe AI that could be safely released to users? Who want to go first? Maybe Maruyama Sensei? You mute.
Okay, I think my position is that for the first one, which is I think that within the current technology, machine learning technologies, still we can have enough engineering discipline that makes the machine learning, usable for the real world applications. And the reason is that the George Box statistician said that every model is wrong, but some models are useful. And I think it is very important for us to identify these useful models instead of trying to create the complete models. So that's my position.
Okay. Anyone else?
Yeah, if I could chime in, I mean, I think in control systems, we view like performance and robustness as two orthogonal objectives, right? And there's no, I think the case is, pretty much closed that for a lot of these systems, you're just, in terms of performance, there's just no way you're going to be these like deep learning based models. So it's incumbent upon us to build either, the infrastructure around it or the actual tools within the learning mechanism itself to explicitly to provide the signals for us that we need in order to build in robustness. So I kind of dodged your question because I think there's like the two paths that you outline are kind of like the two main options, right? But again, I go back to this notion of intrinsic measures of uncertainty, and like the work that we're doing on out of distribution. It really seems to me like those kind of tools, if we can make breakthroughs in those kind of tools, that will be a key enabler to getting these systems out into the real world. All you need is the model to be able to tell you when it's not sure.
Yeah.
And then you're good, right?
You can compensate with.
Exactly. Then you can build the engineering infrastructure around it in order to do whatever you need to do.
Other opinions?
Yep. My take on it is that you still need the engineering guardrails either way, right? So even if you have let's assume hypothetically perfect, model or system. I mean, if you think of like human level performance, like humans make a lot of mistakes, and we still have like, these systems in kind of controlling the bounds of what they can make. I think the problem is like what kind of mistake you're going to make and what application or what domain you're in. So in domains like, let's say surgical robots or domains like where you have a legal system or health system, you have to be scrutinizing the system even more and have a lot of these guardrails at each and every layer. So it's like defense in depth versus in another system where you're making recommendations for, I don't know, music recommendations. The bar is much, much lower, and maybe you can rely on improvement in learning, where you have error minimization to a level where you can say, well, there's some leeway here. But I think either way, you want to be careful about dropping one versus the other. I think it's required but insufficient.
Okay, interesting. I agree. Any other contribution around this? Then my next question to you is, from your perspective, beside the safety will appear to be the obvious bigger challenge that we're facing here if we want to release product. What do you think, from a researcher point of view, like this community, we have a lot of people doing research around this engineering ML systems, so they're trying to contribute with new efficient techniques, new ways to engineer those systems, improve their quality. What would you say is the number one area where people should be looking at, which is, to your perspective, still underexplored?
I don't know. I mean, maybe, very quick thought. I think, as Mohamed was also saying, when we were talking about like maybe the plethora of tools that, we have available for regular software development, and, as much as the ecosystem is growing and, we maybe have the right conditions now, both at the level of underpinning layers, and infrastructure, things on the cloud, things like Kubernetes, that will help grow the ecosystem out. There's a lot of open problems and challenges, right? And I think there are a number of open research problems, but also, there will be, in order for a specific technique to be usable for a model development team, it needs to make its way all the way into hardened industrialized technology, that hardened component that can be deployed, right? So we're and for that matter, maybe a lot of the problems that we've been talking about is just at the level of a lot of data science still uses things that are papers that have been it's specific techniques that have been adapted from papers, right? And the code associated with those papers. So which again is far from a hardened implementation. I mean, we've seen, just like QuantumBlack, like some of the problematics around doing that, right? Like in the context of some of the work that we've been doing in time series forecasting and using, in collaboration with Element AI, like trying to adapt something around NBeats, which was, their specific framework for, time series forecasting, developed around the M4 data set and a specific publication, but trying to take it into a number of other contexts and seeing a lot of the heavy lifting and a lot of the engineering problematics and hurdles that have to be navigated in taking that implementation and generalizing it and making it fit for purpose to sit in a production environment. But I would, if I were to call out two specific challenges. I mean, one, I think there's maybe, Foutse, going back to your point about the underspecification of ML. I think there's need to move into to have much more, let's say, a rigorous underpinning and more platform enablement around how we run experiments. Right? As much as we look at historical performance on the one hand, I think a lot of data science, and for any number of reasons, including around confounds and admitted variable bias, any number of structural points, we want to be able to get to, deployed models where we are looking at the performance of the models, seeing how they behave, perhaps correcting for structural deficiencies on the back of the data that we're collecting post deployment live. But it means that we're much more rigorous about how we A/B test models and how we baseline them. I think a lot of, and I think there's a number of different tools and frameworks and components. Again, I would call out Determined AI and their model registry components as things that are moving us in the direction of improving repeatability around data science, which is great. All of that said, in too many different situations, at least the ones that we see in a lot of different organizations and work that we do, there is too much bespoke code that has to be written around how do I baseline and benchmark a model, and how do I run experiments to be able to look at how if only at the level of hyperparameters, how a specific change in those hyperparameters is affecting performance. Yeah.
Change impact analysis and the others. We definitely need more tools.
Yeah, I completely agree with everything that Jacomo just said. Like, I think like the tools of even just like the tools of containerization for us in robotics have been pretty transformative, right? Because now we can ship software and have a much higher degree of like expectation that on the other end it's going to work without someone having to like disentangle apt-get confusion for 18 hours or whatever. And that's already been like that's the huge enabler for us of the whole AI driving Olympics thing, right? Everything is shipped around as Docker images, and that is so yeah. The notion that at the very least we like hold ourselves to a little bit of a higher standard in terms of what we call science. And I think we're like, it's really moving in the right direction. But there was a period there when when there was a lot of papers that were coming out that were like junk science, like not real science, like not evaluated properly. And I think that as a community, like, I mean, as a research community, as an academic community, this could be one of our roles, you know, where we stand there and say, hey, wait a second, like there's a proper way to do scientific experiments in order to like justify your conclusions, and you know, you haven't met the bar or whatever.
I want to add up a few points. Actually, I agree with Jacomo and Liam, specifically what you mentioned earlier on understanding uncertainty. Like neural networks, deep neural networks specifically are really bad at this. They could be extremely sure of, you know, making a decision, but it's the wrong decision. And if you can anthropomorphize that and think of like, if you have a human or an assistant who's very sure, but they're really wrong, it kind of breaks the trust. And I think trust is extremely important in human-computer interaction, specifically when you're talking about non-deterministic systems. So I think there are two facets to this. The first one is how to reproduce results in terms of like whether you're building on top of somebody else's work, especially now with the explosion of like a lot of pre-trained models, and how can you basically have trust in that implementation, because you're kind of borrowing a lot of logic units into your software, right? Before it used to be libraries that you can unit test and verify, but now these are building blocks of somebody else's models that you're introducing into your ecosystem, into your own solution. The second one is actually more about the under specification of like AI products or solutions. One of the biggest challenges, I think, especially from the industry perspective, when you're talking to customers and clients, they think of solutions just a traditional way, software 1.0. You open up Word, you expect it to work. You check grammar, it just works. You can replace the words. You change the font, it just changes, right? There's some sort of trust in the system just works. And when you're communicating to them expectations about AI, a lot of the times people look at AI solutions as the traditional software. It should just work 100% of the time. Like, why wouldn't it, right? You know, there's no messaging that says, by the way, this probably will work, right? It always like, here's the AI solution that will solve this problem. I think language is very important and expectation management is very important. And this goes all the way back to like specifying what is it that you're trying to solve. You're trying to solve a problem. You're not just 100% communicating that it's going to work. This is, I think, the trustworthy computing that has been, you know, a very important goal for the industry. And we've worked collectively so hard to establish like your trust in putting mail in the cloud, your trust in banking online. Now we have to think about like trust in working with AI.
That's a very interesting, very good point, actually. It's often overlooked, the things we're doing. That's very...
Yeah, if I can chime in on that, I also really agree with that. And I think that's an excellent point. When it comes to like human-machine interaction, I think we should always keep in mind that there's like two options. We can like make the machine really good, or we can educate the human to expect like and mitigate their expectations. And if you take the autonomous car as an example, the successful, by and large, the successful like autonomous car deployments are like these shuttles that move really slowly, and nobody like expects like them to do anything crazy. They don't expect them to behave like people. They understand their operation. It's like there's a contract between the people and the system. The people accept the system as being like suboptimal, but they are happy to trade suboptimal for like repeatable or like predictable or whatever. And so there's like on the like multi-objective optimization of all of these systems, there's so many different factors that can all be considered. And the application that you're in, you might need to consider these different factors and weigh them differently, right?
Yeah, definitely. Maybe one last point from the panel. Maruyama Sensei, you want to chime in?
So I completely agree that the expectation control is very important, and I think that is related to the requirement development. So how you get the requirement from the customer, and the customer usually don't know what they really want. Okay, and for example, if you are talking about the self-driving car, of course, safety is important. But if you want to have 100% safe car, then the car doesn't move, right? Because right. So the customer has to be explicit that what kind of risks about the safety I can get, right? Is in the cost of the, get the benefit of the moving cars. So I think it's very important to have more, discipline in requirement development, and we can get some help from the software engineering community.
Yeah, definitely. I think our colleagues in the requirement engineering have a lot to contribute in this space. I think we're way over our time, so it was so very interesting. Couldn't control for the time. I think I got the okay from Kaz to go a bit over time, so I think we're good. Unless there is any specific last question from the audience, I will thank you, everyone. Thank you very much for the very lively discussion. Thank you for all the inputs. And I will pass the baton to Kaz. Kaz?
Thank you for great discussion for panelists.